morning, Earthlings! If you follow the channel, you know that we are resurrecting the Apollo communications system with original spacecraft and NASA ground equipment. In the last 2 episodes, we were finally able to get down voice working, which was a complicated affair and taught us a few things about PLL circuits. Hello, hello?
Hello, hello.
Hello? Oh, it's working both ways?
Yes.
Alright, excellent. So at this point we have up voice.
Hello, this is Houston.
Down voice. The emergency Morse key. And not to forget TV from lunar distances, all working.
TV from the moon.
Not bad. We also had figured out the mysterious, undocumented and very steampunk looking up data link test box, which transmits commands to the spacecraft via punched paper tape of all things. We got it all going and could hear the received modulated signal on the spacecraft side. But we have not yet decoded the transmitted up data. For that, we need to add the aptly named UDL or Up Data Link box on the spacecraft side, and that's what we are going to work on today.
Alright, so Mike, what do we have on the bench today?
This is the Up Data Link assembly, which is the box that took in commands from the ground and decoded it into either relays to be switched for the spacecraft, or new time for the central timing equipment, or commands to the Apollo guidance computer.
It's the remote control box. It's the RC box that you could play with command module.
Yep.
So we're going to open it up, see what's inside.
Is there pressurization?
Is it under that little cover there? Next
Yeah,
to
it's a tube. This is a tube. So we looked at it. It's a brazed tube. It doesn't seem to be a Schrader valve.
So this is just another connector.
Yeah, it's a smushed little connector.
Didn't see a Schrader valve, didn't see one on the bottom either.
No. That's the only thing.
Nope, okay. You're the one that loves opening stuff up with a million screws.
It's a lot of hard work.
You do it. Yeah, the one I tried wasn't too bad.
What size is that?
7/64.
No more screws?
No more screws.
Did it open?
Nope, not yet.
Did you hear something escaping?
No.
Oh, there you go.
Is the pressurizing?
Okay, good.
Nice.
There you go. Done.
Hey, look at that.
Onto the glowy gloves. Oh yeah, it's
Is it
attached
tied up?
here. So we have to bring the connectors. It's like the PMP.
How do you do precious piece of NASA equipment with improvised tools?
Okay.
That can't be metric. It's neither metric nor
What other system?
Nor imperial. it's alien. There you go. It's going to go a lot easier. Oh, and one connector suddenly disappeared. And the test connector is annoying you?
I think so.
Oh, is that the one?
Yeah. What? Woo! Yeah, there you go. Okay, it's 3. Rattle.
Oh, I see good stuff.
What am I caught on there?
The connector.
Oh yeah. There we go.
Wow.
Woohoo! Oh, it's all potted.
Those modules.
No,
are
they're the
great.
Motorola modules. They're Ken's favorites. Oh no, this is Ken's worst nightmare. These look like the flight version of the undocumented Motorola logic modules that he found in the ground up data link test box. He somehow managed to find out what they did by testing them on a breadboard, but he finally got confirmation of what he suspected they were thanks to the 3D X-ray machine from our friends at LumaField. They contain conventional discrete components arranged in a cordwood fashion to form early and compact logic modules, sort of the missing link before the integrated circuits took over.
They are.
Yes!
Exactly what they are.
Flip-flop. So he knows them already, all of them. Oh, this is a Motorola box. Well, it matches the UDL. The uplink, the test
Yeah.
box, right? Oh, that is unexpected. The same white wires that go everywhere that Ken loves.
Well, there was a report about designing the UDL with integrated circuits, and I guess that was not something that they ended up flying.
So what are these? Oh, these are feed-throughs. Those are caps or diodes?
They remind me of the filter that
Yep.
we had to replace on the
Yep.
test equipment.
AC filters. But this is not powered by AC, is it? Some PCB. And you think those are the relays? The spacecraft relays?
I think so. It seems likely.
Yeah, lots of relays. And beautiful lacing. Always white wire.
And we have liftoff. Wow. So presumably that.
So it
plate
opens
is
like a
switched
book.
right off.
It opens like a book. The problem that we saw before is that the two boards are stuck together by the conformal coating. So what I can do now is pull a sandwich. But what I cannot do without being very hard on the hardware is separate the two boards of the sandwich. Or maybe if I twist it a bit, I can get it loose. Yes, got it.
Coming out.
Alright. Done right. Here's your sandwich. And then you're none the wiser, right? Because you need to separate them. And they are
They're glued.
stuck to each other. So the issue with those is those two boards have been assembled then dipped in conformal coating, which means the top modules are the top of the module is stuck to the board. And I was able to do a blade on one row, but you have to get all the rows in the middle. That would be very hard to take apart.
And then A105.
That would probably be the assembly number.
So it is not possible to take this apart any further in an attempt to reverse engineer it. We'll cross our fingers and hope it still works, like most of the Apollo flight hardware we've tried so far. But an obstacle stands in our way before we can integrate the UDL in our setup: the high-density Deutsch connectors, a German-made metric connector. These are unobtainium, although TE Connectivity would gladly make us a couple more for a mere $100,000. These would have been prohibitively costly for Samtec to retool for us too. So instead we'll rely on the generosity of one of Samtec's vendors, Hyrox, who let us use their latest metrology machine to measure the connectors. We'll use that to make our own kludge connector.
We can also give you pictures and images directly from the machine as well, or video as well, if you're interested.
Well, I will do.
Diameter measurement, things like that.
Yeah, that's the little connector that got squished. You can see how much it has been squished.
Yeah, the circumference there. It's a little off.
Many thanks also to our friend and mechanical engineer Rob Lyon that made engineering drawings out of the Hyrox measurements. It took one more friend, Philip Frieden of EBTKS Boards and Flip Pins fame, to help us out. He has a CNC that could machine an ersatz insert for us. Thanks, Philip.
So this is the pin end of it, and what you want is the socket end. And so the socket pins have to go into something that aligns them perfectly with that. So I made 2 of them, prototypes and proof that I can do precision drilling.
Okay. Nice beehive pattern.
Right.
So this is a Deutsch connector that's impossible to find.
Yeah, so we'll make it ourselves.
So impossible that at least the American program had to go to Germany to find somebody that could machine that. Because you see how little material is left around the pin, and it's metric.
I think the choice is either something where we're forcing the pins in with a press, or alternatively drill the next drill size up and glue them in with epoxy or something. And we haven't quite finished. There's one last thing. By request, I brought you some flip pins.
Oh, the flip pins!
For building IC replacements.
And so that would have been so convenient in my HP Nixie thing where I replace all the ICs.
Yeah.
And the flip pins is after Philip?
Yeah.
It's a Philip pin.
Well, Flip is my nickname.
All right.
Okay, thanks to a lot of help, we think we have the connector problem under control. The next step was to spend the big bucks to have the National Archives scan the documentation they have had for years about the UDL, and of course never scanned. At $4 a page and hundreds of pages, most of them irrelevant, it gets very expensive very quickly. But to our delight, it included a pinout, which we think is representative of our unit. A flurry of wiring activity ensued, and it was time to try our UDL out.
Alright, so we have the full crew today, and so Mike, Ken, and Eric, and we were all looking at one schematic.
The giant updata schematic showing the function of the updata box there.
And what does the updata box do?
Well, you send data up to the spacecraft, and the updata box will send it to the computer, or you can set the clock, or you can flip different relays. You can send test commands. You can also inexplicably send text.
Okay, and that's the box. It's behind here. I can't really see it well, but we just wired it up. We opened it up first and figured out that we couldn't do anything with it. It's all stuck together. It's very impressive inside. So that's our new UDL box, and that's the remote control basically for the spacecraft, right? From the on the way up.
Yeah. So this essentially let the ground type keys into the DSKY,
Right.
more or less, and also they had their own version of a lot of the switches on the panel, so they could set switches in lieu of the
Right, and
astronauts.
actually override the astronauts, right?
Right.
All of those switches on the control panel, many of them have a ghost switch behind it that's controlled by the box. So if Houston wanted to flip a button, they would have precedence, and then there's a button somewhere to reset it. Right. So if you don't like what the ground or the Russians are doing to you, you just flip the reset.
But not all switches can be reset that way.
Really?
Only some of them can be reset with that switch.
Okay. And then
Three quarters of them can. The first 5, I think, can't be.
Huh. Okay. Are we ready to power it up?
I think so.
Okay. Let's do it.
Before we do that, we need a little refresher about the updata encoding from episode 14, so we know what to expect. Each uplink digital command consists of at most 10 octal digits, so 10 numbers going from 0 to 7. In other words, it's a 30 bits command word. To guard against transmission errors, our 30 bits are not transmitted as is. Instead, each bit is encoded as a distinctive pattern of 5 sub-bits, sending a certain 5-bit pattern for a 1 and another one for a 0. This way, the UDL can detect transmission errors if a non-conforming subbit pattern is received. So the transmitted message is actually 150 subbits long. None of this is fast. The command word is transmitted at 200 bits per second, so the actual subbit stream is 5 times that at 1 kilobits per second. The subbits are then used to modulate a 2 kHz tone to generate a coded audio signal using a method called phase shift keying, or PSK. PSK is a basic method for encoding digital information on an analog link by encoding the bits in the phase of the signal, which results in this weird-looking audio signal. An updated version of this is still widely used today by your cell phone. To aid the UDL in decoding the signal, a 1 kHz reference tone is also added to the signal. This results in an even weirder audio signal. It sounds like this.
There we go.
The continuous tone is the idle signal, and the short lower tone bursts are our 150 subbits whizzing by, while the loud mechanical rattle is our paper tape reader reading the next command before sending it. This audio signal is then transmitted by our Apollo-Com system, a complicated scheme of FM subcarriers and PM modulation. On the spacecraft receiving side, the Apollo transponder and the PMP feed the UDL with the recovered audio signal. The UDL first job is to extract the subbits and the bits from this audio, and that's what we are going to have to test first. Of course, the UDL has much more to do than that. It has to check whether there were any subbit transmission errors, decode the vehicle address to make sure the message is addressed to itself, decode the command and decide whether it should activate a relay, set the system clock, be fed to the AGC, or is simply a test of the system. It is quite amazing that Motorola was able to accomplish this without any ICs. Anyhow, the first step is to see if the UDL can recover our digital bits from the PSK audio sent across the cosmic chasm. And for that, we first need to bring up the whole system.
That one is so much to turn on. 28 volts on.
I don't think this gets power until we switch up that.
Carrier. Because we haven't turned off the transmitter yet. And first things first is to double lock. Give me transponder. Transponder 1. Got you. Now I'll try to lock it. I have to sweep a little bit. There you go. I'm locked. Oh, no, we're locked. We should have some indication. Yep. Don't turn anything on yet. Now we have to get locked on the way down. We have.
Hey.
Okay, it's locked.
Perfect.
Now, if you give me some voice.
Hello? Hello? Hello?
Oh yeah, I have you. Oh, you don't have me. No, this is because I haven't turned the modulation on yet.
There we go.
Apollo, this is Houston.
Oh.
Oh. Okay, so it works this way. So we have voice and TV, and so now we need up data. Okay, up data box is on. So that's
Should have
my
the
old
data.
test tape of data. So click stop. What do we do next?
Do we turn on the?
Do we have a way to check that the thing gets us some life?
We can look at the UDL data, the subbit data.
So let me turn data on. Actually, I don't even know which level I should be at, and I should be able to hear it if I do backup. Yeah, that was
So it's
that
there.
was data. I have plenty of it. Don't know if I'm translating too much or not enough. And right now it's idling.
The UDL is turned off.
Are we ready to turn the thing on and see what happens? Turn it on. Yeah,
I see data.
I see bits.
Little bits.
There you go.
Huh. What's the default state? Does it just stay in a one state?
I think when you turn it on, you got a few bits. So let's redo it again. I think it just tried to take a few bits. Yeah, it does a few bits and then it stops. It has life.
Why would it stop?
I saw digital bits. I don't know. You want me to give it something?
Yeah. Yeah, I saw something.
You got something?
Yeah. Yeah.
And it should happen before it goes ticky ticky tick.
Yeah.
Yeah,
Yeah.
we got data.
Yeah.
All right.
Yeah,
Got
there
it.
you go.
Okay,
There we
so
go.
we have bits.
Genuine bits.
Excellent.
Can we check we got the right ones?
Okay.
Command 4632.
Do you have the table of what subbit code is?
Guys, we need to do the little Usagi Electric dance of victory here. We have bits coming up for the first time. And Eric has a table of subbits.
Oh.
Each bit
Got it.
is encoded as pattern of subbits. One for ones, one for zeros, and there are two versions of it. One for the vehicle address and one for the rest.
I think the polarity is inverted. So that's
No, I think we have 00100 first, with the narrow one, and then 11011 with the two wider ones.
and then what's the next set here? Because this would mean that it's switching to the different sub-bit encoding
Yeah.
after only 2 bits.
Yeah.
And I'm expecting to see 3 bits for that first
Right.
vehicle address code.
Yeah, it's not making sense to me here. I mean, we should never get that many ones in a row. So something's definitely messed up.
That doesn't make any sense.
Exactly.
Something's not right.
Okay, not bad, we have life, we see bits. We are receiving something, but apparently not decoding the right thing. I have a feeling it might take us another episode or two to sort this out. In the meantime, I'll see you in the next episode.